Hello, class. The purpose for this online video lecture is to derive the first law of thermodynamics for a control volume, an open system where mass is able to enter and leave. We're doing it this way so you can focus on reviewing this material outside of class, and then in class we can work in groups to actually put this into practice and see how it applies. And before I get started here, I want to give a shout out to my late great dean, Phil Gerhardt at the University of Evansville. May he rest in peace. He was a great teacher, a great lecturer, and a lot of this material I learned to present from him. I want to give him a shout out. Okay, since this is the first law for a control volume, we definitely want to start by drawing a control volume. And I'll do that with just a generic maybe bean shape. I don't know why we draw beans, but there it is. And I'll label that my control volume. And this is an open system, so hopefully we understand that now mass can cross the boundary. So here's a mass flow rate in, and we can have mass flow rate out. And we can have multiple mass flow rates in, multiple mass flow rates out. That's not a problem. And we also have different ways for transferring energy across the boundaries. One mode is heat transfer. So there's some heat transfer going out. Here's some heat transfer going in. We could also have work. That could be, for instance, work on a shaft. So think of that shaft spinning, and that would be rate of shaft work coming into my control volume. I could also have, for instance, electrical work. So I'll draw a rate of electrical work occurring as well. All of those things, regardless, we know that energy is conserved. So that's one of our first principles here. And this is very much an accounting problem. We're accounting for energy. And conceptually, what we're doing is taking the sum of all energy entering my control volume, subtracting the sum of all energy leaving my control volume, and the difference must be the change in energy stored inside my control volume. Okay, let's get a little bit more mathematical here, and let's write this in terms of time, a time rate. So here will be the sum. Now energy, I'm talking about my extensive property and the rate of it. So there's capital E dot. So there's the rate of energy entering my control volume. Here's the rate of energy leaving my control volume. And that must balance with the time rate of change of the energy stored inside my control volume. Okay, let's talk about the left-hand and right-hand side here conceptually. So on the left-hand side, I have energy flows, things crossing my boundary. Well, energy flowing across my boundary. And now I have three possibilities. I have heat transfer as one mode. As a second mode, I have work. And now as a third mode, I have energy being carried by mass as it flows across the boundary. So energy carried by mass. I'm talking about a rate, so time rate of energy. And if it's carried by the mass, that would look like the mass flow rate times the intensive energy. So again, this is energy per unit mass being carried in by the fluid as it flows with a certain rate. So on the left-hand side, I have energy flows. On the right-hand side, I have energy storage. And I can write that total amount of energy in my control volume as the mass of the control volume times the specific energy of that control volume. Note that I don't have m dot. That's not a mass flow rate. I still have the time derivative on it, which is where I'm getting the time derivative. So that's the time derivative of the mass stored inside the control volume. Okay, let's use this and put it together. So I will move down, and I've got now the sum of all heat transfer entering plus the sum of the rate of all work coming in. I also have the sum of all energy being carried by the fluid as it's entering. I need to subtract everything that's leaving, so I'll subtract all rates of heat transfer going out. I'll subtract all rates of work going out. I'll subtract the rate of all energy being carried by fluid as it leaves. And then on the right-hand side, I have the time rate of change of the energy inside my control volume. Left-hand side, what's crossing the boundary. Right-hand side, what's happening inside my volume. Well, let's remember our definitions of the directions of heat transfer and work from our historical usage before we knew that they were both just forms of energy transfer. We will say the sum of the rate of heat transfer in minus the sum of the rate of heat transfer out equals Q dot. So positive rate of heat transfer is coming into my control volume. Remember, we historically have thought of work in the opposite in terms of directions, so we're going to let the sum of the rate of all work being done out from our system on our surroundings minus the sum of the rate of work being done in other words, from the surroundings on the system. We'll call that the rate of work net. So we're saying a positive rate of work is work that's being done by the system on the surroundings. So the same sign convention as we used previously for control systems. I know that's confusing, but it's historical. Before we knew that heat and work were both forms of energy transfer, we just built steam engines, and we knew you put heat in, you got work out. So we called heat in positive, work out positive as well. Let's incorporate that. Now, so then on the left-hand side, we have the total rate of heat transfer minus the total rate of work. Let's see here. Then we're going to have, I still have these leftover mass flow rate terms. I'll move them over to the right-hand side. So I'll have the sum of energy leaving by mass flow minus the sum of energy entering via mass flow and the time rate of change of the energy inside my control volume. Okay, let's explore the energy terms on the right-hand side a little bit further. To do that, let's look at the sum of mass flow rate times specific energy. Well, that's occurring over a portion of the boundary. So really what I'm saying is it's the integral of the specific energy with respect to the changing mass flow rate across a boundary. Let's peel this apart a little bit more. Really what I'm saying there is the area integral of energy. Okay, specific energy. In this course, I have three components. That could be specific internal energy, plus specific kinetic energy plus specific potential energy. So I've taken my energy and I've broken it into its three possible categories. And then what's left, I have the differential mass flow rate. I can write that in terms of density, the speed component across the boundary, or normal to it, and the differential area. Okay, and the other type of term I have is the energy storage inside my control volume. So there's mass times energy inside my control volume. What I'm really saying here is this is a volume integral of energy. So there's internal plus kinetic portion plus potential portion times mass. Mass would be density integrated over my volume. Okay, so I've got a more accurate way of describing the forms of energy crossing my boundary and the form of energy being stored inside my control volume. I've written those in terms of flows across a differential area and storage inside a integrated volume. Let's talk a little bit more about work. Hang with me and we'll be putting all this together in a little bit. Hopefully it should make sense. We'll let work be conceptually defined as a force occurring over a distance. And we can speak in terms of a rate of work, being force times a rate of motion, which would look like a velocity. Now let's note that the flowing of the fluid is going to do work. So it does work on the surrounding fluid as it enters or leaves the control volume. So the flowing does work. I'm going to call this flow work conceptually. Let me try to draw a little schematic here to try to explain this further. Here's my control volume, and let's consider a little packet of fluid as it's entering. So there's a little differential packet of fluid, and it's having to push its way in. So I would call that negative work occurring. And on the other end, I have a little packet or piece of fluid on the inside that's pushing its way out of the control volume. And I would call that positive work that's occurring. How does that really work? Well, let's look at a packet of fluid, and I'm going to draw a packet of fluid here. Okay, that packet of fluid might be moving with a certain velocity, so I'll give it a velocity vector looking that way. Okay, and then here's the normal direction. And then remember, my control volume is associated with the fluid. Fluid's going to be at a pressure. So the other thing I have going on is a pressure on that fluid element. Remember my definition. So for differential work of a fluid, that would look like force times a differential distance or displacement. Well, this is a fluid, so I can describe the force in terms of the pressure on the fluid over the differential area of the fluid. And then the displacement, well, the displacement as it pushes its way in and out, that differential distance is going to look like the dot product of the velocity vector with the normal vector. In other words, the normal velocity component multiplied by the differential time. And let's start trying to make this look like something we've seen before. Let's divide both sides by differential time. So now, on the left-hand side, I have the differential rate of work being done by the fluid. And let's see, on the right-hand side, I have pressure times differential area times the normal speed. Let's see, let's try to get some density out of this. So I could write this in terms of pressure over density times normal speed times differential area. And then, well, density times normal speed times differential area. That's a differential flow rate. And furthermore, the inverse of density is specific volume. So my rate of work of the fluid as it's entering or leaving my control volume looks like a pressure times a specific volume and differentially times a differential flow rate. I've taken the concept of work, force times displacement, and for a small differential packet of fluid entering and leaving the control volume, I see that I have a way of describing that as a work term. And I can analyze that in terms of the mass flow rate, the specific volume, and the pressure of the fluid. Okay, if that's true, then my total work, going back all the way here to the top, I have forms of work, shaft work, electrical work, for instance. It appears I also have a form of flow work. So let's keep track of all of these things together. So I have total work would be forms of shaft work, electrical work, for instance, plus the rate of work of the fluid. And I've just said I can write that as the sum or the integral of pressure times specific volume with respect to mass flow rate of everything entering, which I define as negative, and the mass flow rate integral of the pressure times the specific volume of what's leaving, out. Okay, so I've peeled apart new forms of work occurring, flow work, and let's incorporate that back into our conservation of energy equation. Okay, I'm going to take this and I'm going to incorporate what I've just learned about work, bring it all together.